Sauce here. This is a video lesson on transformations. Transformation means change. And what we transform in mathematics is we transform equations, we transform functions, we transform the graphs of those functions and equations. So we're going to think about transformations by defining a function, x cubed minus 3x squared plus 5. The graph of this function is a bit sophisticated. It looks approximately like this. In general, we could think of an equation y is equal to a function of x. We could think about the ways in which we could change the graph, and the ways in which then the equation would change to make the graph change. There are many different ways in which we can transform. One, we could say or call translate. Translate is a fancy word for slide. Visually, what it means to translate is to take the entire graph of the function and move it horizontally or vertically. Horizontal transformations or translations are slides to the right and left. Every point in the graph would move. We could also translate vertically in the two directions up and down, which means moving all of the points by the same amount up or down. And we can accomplish a translation or slide in any direction as a combination of those two. If we wanted to go down and to the left, we would go down independent of left, and then together they would look like it went in an oblique direction. So the two ways that we can translate, we can call right and left, which are descriptive words for a horizontal transformation, which affects the horizontal variable, often x. The two ways that we can transform vertically, we call descriptively up and down. And translations that go up and down affect the vertical variable we often call y. So if we had a function, any function, in general we could say y is equal to f of x. Then we could describe a translation up by a specific amount 5. And the way that we would transform the equation is that an up is a description of a vertical change, so we would modify the vertical variable y. And how do we modify it? It's counterintuitive. To move up, we subtract from the vertical variable. And because we're very often used to seeing equations that we graph solved for y, this is equivalent to adding 5 to both sides and putting it in the form y is equal to f of x plus 5. If we were working with this equation, then the equation would become x cubed minus x squared plus 5, and then we would add 5 again to get the equation x cubed minus 3x squared plus 10. Another translation we could describe as right by 3. A right slide is a horizontal change. So we're going to modify the equation by doing something to the horizontal variable x. In this case then, we leave y on the left by itself, and if we're going to show a change on x, then we need to group our change with the x variable. To move right by 3, it's counterintuitive. We think of right as the positive direction. To move right, we subtract from x. It's already solved for y, which is typical for graphing form. So what would the actual expression for f look like if we're going to move the whole thing right by subtracting 3 from x? Well, we would need to subtract 3 from x before cubing, then minus 3 times subtracting 3 from x before squaring, and then plus 5. There are other types of transformations. We can call the family of transformations that distort a dilation. Dilations can be done vertically and horizontally, and we can distort by compressing distances or stretching them. A dilation that we describe as a stretch increases distances, and a dilation that we call or describe to be a compression decreases distances. What that looks like, which is best done with modern graphing software, but we can show it. If we wanted to dilate vertically, then we would perform a compression or vertical compression by decreasing vertical distances. The vertical distance is the distance from a point to the x-axis. So a point on the function up top has a vertical distance, which would be the distance from that point down to the x-axis. And if we imagine decreasing that distance, we could show that distance as halfway, like that. This point here, I could compress its vertical distance by a factor of 2, or halving it, by showing the full length and then taking half of it. A point that is on the x-axis has a 0 vertical distance. The y value of a point on the x-axis is 0, so it doesn't compress or move anywhere. A couple of points can guide how this function would look after it's been vertically compressed. How do we do that mathematically? In general, we could describe a dilation, in this case, I'm going to call it a vertical stretch, which would increase vertical distances, and describe it as a vertical stretch factor 2. Vertical distances are going to double. How does it affect the equation? It's a vertical effect, so it's going to affect the vertical variable y. And it's counterintuitive. When we think of stretching, we think of multiplying. But to get vertical distance to stretch by a factor of 2, we divide the y variable by 2. And if we wanted to solve for y for graphing purposes, then we would clear the division by 2 by multiplying both sides by 2. That means that if we are working with this expression here, then we would multiply the entire expression by 2 to perform a vertical stretch by a factor of 2. Let's do one more. Let's consider a vertical compression. And at the same time, a second transformation, because we can do as many as we wish all at once, of left by 4. How does it affect the equation in general? A vertical compression is going to affect the y variable, the vertical variable. Compression, we think of, it shrinks distances. And to shrink distances, we think of division. But we accomplish it counterintuitively by multiplying. So we're going to multiply the y, or vertical variable, by 3 to affect a compression. Left is a horizontal change. So we're going to modify x. We think left goes in the negative direction, but it's counterintuitive. We have to add to go to the left. How does that affect the equation? Well, I could solve for y first by dividing both sides by 3, or multiplying by a third. Taking the expression for f, that would then be 1/3 times the entire expression that I'll put into large parentheses. But I also need to add 4 to x before cubing and before squaring. There are a couple more transformations. We can reflect, which we accomplish by making variables negative. We'll look at that in future lessons. We can rotate. Rotating algebraically with equations is difficult and challenging and will be beyond the scope of this course.